Welcome to an elementary synthetic geometry-based introduction to inversion of the real plane with respect to a circle course, episode 9, lecture 9, with which we conclude the theoretical study of the material of this course, and in which we prove the remaining 8 theorems which partition the remaining material for this course as follows. Across the theorems number 37 and 38, we will see that inversion of the real plane with respect to a circle with any power, positive or negative, preserves the tangency points between a circle and a straight line and between any two circles, provided that the tangency point is distinct from the center of inversion. Across the theorems numbered 39, 40, 41, 42, and 43, we will investigate how inversion of the real plane with respect to a circle acts on the so-called orthogonal circles. And for the proofs of the theorem number 39 and 40, as a fair warning and as a heads up, you will need a firm grasp of Euclid's Elements, Book 3, Propositions 36 and 37. These two theorems are the converses of each other, and they're known as the second tangent or tangent second theorem and its converse. Then we will solve the problem number 10, in which we will address the remark that we made earlier in the course, that when a circle is taken into a circle under the corresponding inversion of the real plane with respect to a circle, then the center of the circle that is being inverted is not taken into the center of the image. However, in the problem number 10, we will find a way which will allow us to execute certain number of steps and invert the center of a circle into the center of another circle that is the image of the original and vice versa. This is an interesting problem to think about on your own. Next, we will look at the notion of the power of a point with respect to a circle, and we will cover the three cases when the point of interest is located strictly outside, exactly or precisely on, and then the third case is strictly inside of a given circle. And in connection with the power of a point with respect to a circle, we will also introduce another notion called the radical axis of two circles. And in the final theorem of this course, the theorem number 44, we will prove that the radical axis of two circles is a straight line that is orthogonal to the line of centers of the circles. Then in the final section of this lecture, we will look at the practical side, and we will learn how to construct the radical axis of two circles regardless of the mutual juxtaposition of the circles. And as the very final segment of this lecture, we will realize that the radical axis of two circles is actually the home of the orthogonal circles of two given circles. Again, if anything is not clear or you missed something, feel free to ask the question in the comment section. And overall, this particular lecture is based on the chapter number 9 of my free Inversive Geometry for All book. The link to this chapter is in the comment section. Click on that link, pop it open in a tab in your browser, and read along as we go through the lecture, for example, or after you watch this lecture and something is still not clear, you can go over that chapter in the written form. According to the theorem number 37, if a circle Q and a coplanar straight line L touch each other at a point T that is distinct from the center of inversion, then under the corresponding inversion of the parent plane with respect to a circle, that point of tangency T is preserved. More technically, that means that if we have two geometric objects, a circle named Q and a straight line L, these two objects belong to one and the same plane, and they touch each other at a point T that is distinct from the center of inversion, which we traditionally designate with the uppercase O, then the corresponding inversion of the parent plane, be that inversion with positive or negative power, so long that of course we understand that the power of inversion is fixed for the duration of the application of that inversion across all three objects of interest, then the circle Q will be taken into its image Q prime. The straight line L will be taken into its image L prime, and the point of tangency of the circle Q and the straight line L will be taken into its image T prime. One more time, I want to underscore the fact that when the images of all the objects of interest, the image of the circle, the image of the straight line, and the image of the point T are obtained, all these images are obtained with one and the same fixed power. All the images are taken with the positive power, or all the images are taken with negative power. Then, according to the theorem number 37, if the coplanar objects of interest, the circle Q and the straight line, touch at the point T, then their images, the circle Q prime, for example, and whatever straight line L becomes as its image L prime, they will also touch exactly at the point T prime, the image of the original point of tangency. And in this segment, we only formulate this theorem, and we discuss this proof after we formulate the theorem number 38. According to the theorem number 38, if two coplanar circles touch each other, whether externally or internally, then under the corresponding inversion of the real plane with respect to a circle, that point of tangency, if it is distinct from the center of inversion, is preserved. Slightly more technically, if two circles, for example, the circle Q1 shown over here and the circle Q2 and the circle Q2, for example, here, shown on the right side of the circle Q1, touch each other internally, as shown over here, or externally, as shown over here, at a point T that is distinct from the center of inversion, then under the corresponding inversion of the parent plane with respect to a circle, whether that power is positive or negative, that point of tangency is preserved, meaning that the circle Q1 is taken under the inversion with positive or negative power into its image Q prime 1, which could be a circle or a straight line. The circle Q2 is taken under the inversion with positive or negative power into a circle or a straight line Q prime 2, the image Q prime 2, and the point of tangency, that is again distinct from the center of inversion, is taken by the corresponding inversion with positive or negative power into its image point T prime. Then, if the circles Q1 and Q2 touch at the point T distinct from the center of inversion, then their images, whatever they are, straight lines and or circles, will touch precisely at the point T prime, which is the image under the corresponding inversion of the original point of tangency T, and both of the theorems 37 and 38, which again, one more time, apply to inversions of the real plane with respect to a circle with both powers, positive and negative, can be proven as follows. First, recall that in the previous lecture, across a series of theorems, we proved that regardless of the mutual juxtaposition of any two coplanar straight lines, the magnitude of the angle that such two straight lines form is preserved under any inversion of the corresponding plane with respect to a circle, be the power of that inversion positive or negative. Moreover, from the so-called fundamental theorem of inversive geometry, the so-called similar triangles theorem, which was numbered as the theorem number 23 in our course, we know that the orientation or the direction of all relevant angles under the inversion of the real plane with respect to a circle with positive or negative power is changed to its opposite. That is why, as the bijection of the real plane into itself, the geometric transformation that we're studying in this course, the inversion of the real plane with respect to a circle, is known as an anticonformal mapping. In other words, any inversion of the real plane with respect to a circle under positive or negative power changes the orientation or the direction of every relevant angle to its opposite, but it preserves the magnitude of such angles. That is the part that is important to us. Number two, we know that the point of tangency of any two not necessarily coplanar curves is unique in the sense that if two curves intersect or if two curves touch, they necessarily touch each other at precisely one point. Not 2 points, not 3 points, not 17 points, but at one, precisely one, and exactly 1 point. And from the combination of these two facts, the fact that inversion of the real plane with respect to a circle under positive or negative power preserves the magnitudes of all the relevant angles, and the fact that the point of tangency of any two curves is unique in the sense that I explained, the proofs of the theorems number 37 and 38 follows. Why is that? Well, from the fact that inversion of the real plane with respect to a circle with negative or positive power preserves the magnitudes of the relevant angles, the following observation follows. If two coplanar curves are positioned with respect to each other in such a way that they form a certain angle, whatever that angle is, then the images of these curves under the corresponding inversion of the corresponding plane with negative or positive power will be positioned with respect to each other in such a way that they will form exactly the same by magnitude angle. Now, when two curves touch, and in our case, it could be two circles or a circle and, as we saw in the previous theorem, a straight line and a circle. They do so again at a single point, but first of all, when this phenomenon takes place, then the angle between two such curves is what? It's 0 radians. It's 0 radians or 0 degrees. 0 radians or 0 degrees, but again, it doesn't really matter. What matters to us is the fact that the magnitude of all the relevant angles under the inversion of the real plane with respect to a circle with positive or negative power is preserved. That means that whatever the images of the original curves are, whatever the image of the straight line L and whatever the image of the circle Q, or whatever the image of the circle Q1 and whatever the image of the circle Q2, when the images are taken or constructed, then the angle that they will form must, again, by the first observation, be 0 radians or 0 degrees. And here, this is what we carefully state. From the second observation, or from the fact that the point of tangency between two curves is unique, it follows that such a point, for example, the point T shown over here, belongs to, by the virtue of being the point of tangency, it belongs to two curves at the same time at once. But in the theorem number 6, recall that in the theorem number 6, we proved that the image of a given point under the inversion of the real plane with respect to a circle, be the power of that inversion positive or negative, the image of that point is unique. There is only one point that is produced by such an inversion. And that means that the point of tangency T under any corresponding inversion will be taken into an image that is also unique. And by the virtue of being unique again, that point will belong both to the image of one curve and to the image of the other curve. And that essentially means that precisely the point of tangency is preserved. As the summary, the proofs of the theorems 37 and 38 follow from the following two observations. The magnitude of the angles under any inversion of the real plane with respect to a circle, be the power of that inversion positive or negative, is preserved, and the point of tangency of any two relevant coplanar circles is unique. If anything is not clear or you missed anything in the proof of this theorem, then by all means do ask a question in the comment section. Meanwhile, we will move on to the next notion, or the notion of orthogonal circles. As a definition number 5 of our course, two coplanar circles are called orthogonal if and only if the angle between the two tangent straight lines drawn to these circles through any one point over which two such circles intersect is right. From that definition of orthogonal circles, a number of interesting properties of orthogonal circles can be deduced, but such properties are not of much interest to us. One such property, by the way, states that two coplanar circles are orthogonal if and only if the centers of two such circles and the 2 points over which two such circles intersect belong to one and the same circle that I did not show on this diagram, but that circle is there nonetheless. And to avoid the clutter, I did not show that circle. And another property of orthogonal circles that will be of practical interest to us is the following. Two coplanar circles are orthogonal if and only if the radii drawn from the centers of the circles to any one point over which two such circles intersect is right. And that property can be deduced from the definition number 5 as follows, as the basic outline of such a proof. So by definition number 5, our two circles, let's say circle Q1 and the circle Q2, are orthogonal if and only if the angle between the tangent straight line tau 1 drawn to the circle Q1 through one of the points over which two such circles intersect, and the tangent straight line tau 2 drawn to the circle Q2 through the same point is right. And what does that mean? Well, by definition, that means that the radius R1, for example, of the circle Q1 must be what? It must be perpendicular to the set tangent straight line tau 1, and by our definition number 5, that tangent tau 1 must be perpendicular to the tangent tau 2. And from here it follows what? Well, we have two straight lines, the straight line R1 and the straight line tau 2, both perpendicular to one and the same straight line with the corresponding theorem from Euclid's Elements Book 1. It means that these two straight lines must be parallel. The straight line R1 must be parallel to the straight line tau 2. The trouble is both of these straight lines must pass through one and the same point. So bringing in perhaps the heavy-duty Playfair's axiom, which states that in the Euclidean geometry there is precisely one straight line that can be drawn parallel to another given straight line under the condition that the given point is not on the original straight line. So here we can construct any straight line. For example, again, I'm not going to show that straight line to avoid the clutter. We pick any straight line parallel, for example, to the tangent straight line tau 2, and we can fix this point over here, the point over which two circles intersect, and then through this fixed point we must have two straight lines that are parallel to each other, and they must be parallel to some arbitrary straight line. Obviously in the Euclidean geometry there can be drawn only one such line, which means that the radius, the straight line R1, the R1 must belong, let's say, or contained by the tangent straight line tau 2. Likewise, by the symmetric argument, it can be shown that the radius R2 must be contained or belong to the tangent tau 1, and that is exactly the situation when the radius R1 of the first circle is perpendicular or orthogonal to the radius of the second circle R2, provided that both radii are drawn through any one point over which two such circles intersect. And as a good exercise that I will leave out of the scope of this course is for our viewers to prove that such an angle, actually whatever that angle is, does not depend at which point this angle is measured across the 2 points over which two circles intersect. And in this course, we are mostly interested in precisely how any inversion of the real plane with respect to a circle with both positive and negative power acts on orthogonal circles, and we will investigate this behavior across the next 5 theorems numbered 39 through 43. Here we pay attention because the previous two theorems that we discussed in the previous two segments, the theorem number 37 and the theorem number 38, apply to inversion of the real plane with respect to a circle with both powers, positive and negative. But the next three theorems, the theorem number 39, the theorem number 40, and the theorem number 41, will apply only to inversions of the real plane with respect to a circle with positive power, not negative power, but positive power only. As such, according to the theorem number 39, any circle that passes through any 2 points that are the inverses of each other with respect to a circle named, for example, C, that has the point O as its center and a strictly positive real number R as its radius, with positive power, again, we're paying attention over here with positive power, is orthogonal to the said circle of inversion C. As a friendly reminder, when you take actually any course, it is a good idea to do the following two things. First, it is a good idea to try to run ahead of the course a little bit, and anytime you hear a theorem, you want to try to generate your own proof of that theorem, or at least think about how you would do that. And number two, it is a good idea to carry out all the practical work discussed in the course on your own or in parallel. That means that it is a good idea to pull up your favorite graphing software and try to carry out the corresponding constructions in that graphing software on your own. As such, in order to help you comprehend the technical essence of the theorem number 39 and in order to help you generate your own proof of that theorem, I've put together a small animation using the free software called GeoGebra, and that animation hopefully captures or visualizes the technical essence and the heart and the soul of the theorem number 39. Please take a look. For a proof of the theorem number 39, we observe that by the premise of that theorem, we're given a circle of inversion, lowercase c, portrayed over here on the left side of your board in white partially. We do not really need the whole circle. And the center of that circle is the point O, which means the point O is the center of inversion. And a strictly positive real number R is the radius of that circle of inversion C. And with respect to this circle, we pick any two, literally any two points that are the inverses of each other with respect to that circle with positive power. With positive power, which means that both of these points are located on one and the same side of the center of inversion O. And technically and pedantically, we take it that the points are distinct and none of these points is the center of inversion or the point at infinity. We will take these points, the so-called, to be finite points. That is the interesting case. Then what is the locus of the centers of the circles, each of which passes through 2 points, such distinct points A and A prime, forgetting for a moment about the fact that we're dealing with the inversion of the real plane with respect to a circle. In general, in vacuum, from the middle school geometry curriculum perspective, where do the centers of all the circles that pass through 2 distinct points live? Well, we know that the set of points which play the role of the centers of such circles that pass through 2 distinct points is played by the perpendicular bisector P of the line segment A prime. That is what? That is perpendicular to the straight line that passes through the points A and A prime and cuts the line segment A prime in half as shown over here with double ticks, and this is the right angle. On that perpendicular bisector P, we pick any point we wish at random. Let's say this is the point Q. And using that point Q as the center, we construct a circle named lowercase q that has the point Q as the center and the radius of which by length is equal to the distance from that point uppercase Q to either the point A prime or the point A. We construct such circle, and again, remember that if 2 points that we picked in our condition are what they are, that means that one of these points is located strictly inside of the circle of inversion, and the other such point, its image, or pre-image for that matter, is located strictly outside of the circle of inversion. So this diagram over here is representative. And what does that mean? That means that our arbitrary sample circle, lowercase q, that passes through two inverses of each other with respect to the given circle with positive power will necessarily cut inside of the circle of inversion C, and it will intersect that circle at two distinct points, out of which we're interested in one. Let's say this one. We name that point P. Now we go back to the fact that we are dealing with the inversion of the real plane with respect to a circle. And what do we capitalize on? On the fact that we're given the points A and A prime are the inverses of each other with respect to our circle with positive power. That means that according to definition 1, for these points, we have the following relationship. The distance from the center of inversion to the point A times the distance from the same center of inversion O to the image, let's say point A prime, is equal to the square of the radius of that circle of inversion. But now we go back to the specific setup and we notice that the length of the radius in this case that is drawn from the center of inversion or from the center of the circle of inversion C to the one point where our arbitrary circle Q intersects the inversion circle C. That distance is R, can be recorded here like so. The distance OP squared. This relationship is correct. Why? Because again, our sample point P belongs to two geometric objects at once. It belongs to the circle of inversion C, and it belongs to our sample circle Q that passes through the inversive images of each other. And now for the last step of our proof, what do we do here? Well, we notice that with respect to the sample circle Q, we can do what? We can apply Euclid's book 3, proposition 37 in this case. This is the converse of book 3, proposition 36, or the so-called tangent second theorem. In other words, to the points O, A prime, and P, we can apply precisely book 3, proposition 37, which claims that if it so happens that the rectangle on the second constructed to the circle Q is equal to the square of the straight line OP that, as Euclid puts it, falls on the circle Q, then that straight line, whose square is equal to the rectangle on the second, is precisely what? Is precisely tangent. It means that over here, the straight line, let's say the straight line OP, the line segment OP, is perpendicular to the line segment PQ. This is the conclusion of the converse of the tangent second theorem, and in this case, the straight line that passes through the points O, A, and A prime is precisely a second of our sample circle Q, and the straight line OP that, as Euclid puts it, falls on the circle Q plays the role of the tangent, and that means that the radius OP of the circle of inversion C is perpendicular to the radius QP of our sample circle Q. And that means, as we showed in the previous segment, when two radii are perpendicular to each other, then the corresponding circles are what? The corresponding circles are orthogonal. And from here it follows that our circle Q is orthogonal to the circle of inversion C, and that concludes the proof of the theorem number 39. If you miss anything, or if anything is not clear, then by all means ask your question in the comment section to this episode. The theorem number 40 is the converse of the theorem number 39, and it states that if two coplanar circles Q and C are orthogonal, if C and Q are orthogonal, then the points Q1 and Q2 of intersection of any secant drawn through the center of the other circle, the circle C or the point O, to the circle Q will be the inversive images of each other with respect to the circle C with positive power. The points Q1 and Q2 will be the inversive images of each other with respect to the inversion of the parent plane in the circle C with positive power if any secant is drawn to the circle Q through the center of the other circle through the point O, and conversely the points C1 and C2, which are the intersections of the secant of any secant that is drawn to the circle C through the center of the other circle, the point uppercase Q, are the inverses of each other with respect to that circle, second circle Q, with positive power. The points C1 and C2 are the inversive images of each other under the inversion of the parent plane with respect to the circle Q with positive power. In plain English, that theorem basically states that if we're given any two circles that are orthogonal to each other, and of course we assume that the two circles at hand are coplanar, they belong to one and the same plane, then, for example, if we stand in the center of one circle, named C, for example, and from that center, the point O, we construct any arbitrary secant that genuinely cuts the other circle or the circle Q at two distinct points, such as the point Q1 and Q2, then these points, Q1 and Q2, will be the inverses of each other under the inversion of the parent plane with respect to that circle C with positive power, And conversely, if we place ourselves into the center of the other circle, into the point Q, uppercase Q, and from that point we draw arbitrary secant, such as this one, to the other circle, the circle C, then the intersections of this arbitrary secant of the circle C will be two distinct points, such as the points C1 and C2, and amazingly enough, it will so happen that these 2 points, C1 and C2, will be the inverses of each other under the inversion of the parent plane with respect to which circle? With respect to the circle Q, again with positive power, because this time the image points, in this case, the points C1 and C2, and in the previous case, the points Q1 and Q2, they all sit to one and the same side of the corresponding center of inversion. Again, we suggest that you try to generate a proof of this theorem on your own, and in order to help you do that, I've put together an animation using the free software called GeoGebra, and that animation hopefully captures the technical heart and soul, the technical essence of the theorem number 40. The proof of the theorem number 40 is not that complicated, and the proofs of actually all the theorems that we will consider in this lecture are not that complicated, and in order to generate these proofs, all we have to do is fish out from our web of mathematical knowledge the pre-existing theorem glue a couple of these theorems together, and voila, the proof is complete. And in this case, what do we have? Recall that in the previous theorem, in the theorem number 39, we were given, in some sense, a fixed circle, the circle of inversion C that was fixed. And then we also, in some sense, varied the circle Q. In this theorem, in the converse of the theorem number 39, or in the theorem number 40, we're given two fixed circles already, and it is the premise of this theorem that it is the case that these two fixed circles are orthogonal with respect to each other. The circle C, the fixed circle C, and the fixed circle Q are orthogonal already. And because these circles are orthogonal, we see that either circle in a way partitions the other circle into two interesting arcs. For example, wearing a hat temporarily that reads a physicist, we make either circle our frame of reference, so to speak, and we reflect the corresponding ambient plane in one circle and see what happens to the points that belong to the other circle. Let's say we step into the circle C, lowercase c shown over here. Well, that circle, due to the mutual juxtaposition of these two circles, will partition the circle Q into two arcs. The outer arc, which is unionized with the 2 points, two distinct points of intersection, and the inner arc will completely produce our circle Q, and conversely, the circle Q will partition the circle C into what? Into two arcs. The outer arc, which when unionized with the two distinct points of intersection of these two circles, and with the inner arc, will produce or complete the circle C. As such, let us say we will construct our line of reasoning based on the view that we have from the center O of the circle C, for example. Then if we construct any genuine secant that passes through that center O and that intersects the given circle Q at two distinct points, the point Q1 and Q2, we already know that if we connect the point O, the center of inversion in this case, with the one of the points where our two orthogonal circles intersect, then the straight line OP will already be, it is known that it is tangent to the circle Q, and to the points O, Q1, Q2, and the point P, we apply what? We apply Euclid's Elements, Book 3, Proposition 36. This is also known as the tangent secant theorem. And according to that theorem, as Euclid puts it, the rectangle on the secant is equal to the square on the tangent. In other words, the product of the distances from this center of inversion to the point Q1 and the distance from the center of inversion to the point Q2 will be equal precisely to the square on the tangent, or the distance OP squared. This is the consequence of the theorem, the tangent secant, or Book 3, Proposition 36 in Euclid's Elements. But this time, when we wrote down this consequence, we capitalized on the fact that the point P belongs to the circle Q. Now we change things around a little bit, and we capitalize on the fact that at the same time, the point P belongs to what? To the circle C. And what does that mean? What does that mean? That means that the distance OP also, in this case, plays the role of a radius of the circle C. So here we can write down the fact that the distance that we have squared is equal to the square of the radius of the circle C, R to RC squared. And that means that because the points Q1 and Q2 are located on the same side of the center of inversion. These points are collinear with the center of inversion, and they satisfy the requirement, the condition 3, actually, of our definition 1. That means actually all the conditions of our definition 1 are honored. And because, again, the points Q1 and Q2 are located on the same side of the center of inversion, that precisely means that the points Q1 and Q2, in other words, if we apply the inversion of the plane with respect to the circle centered at the point O and the radius RC to the point Q1, we will obtain precisely the point Q2, and conversely, if we apply the inversion of the parent plane with respect to the circle C centered at the point, or with the radius RC to the point Q2, we will get the point Q1 again. Notice that our observation about the partitioning of one circle by another into two distinct arcs, the outer arc and the inner arc, plays the role over here precisely. The point Q1, for example, in this case, was sitting where? Inside of the circle C1, and its image under the inversion is taken out, and this is precisely where the point Q2 sits, on the outer arc of the circle Q. Now that we proved the first part of this theorem, we basically almost verbatim repeat this proof when we step, so to speak, into the frame of reference that is our circle Q. Repeat the same argument. I will leave it exercise to the viewer just to make sure that you understand what is going on, but either way you should be able to see that in this case the points C1, which points? The points of intersection of any straight line that goes through the center of the circle lowercase q, or the point uppercase Q, and the circle C. In this case, we will reason that the distance from the point Q to the point C1 times the distance from the point Q to the point C2 is equal to what? To the square of the distance QP, which happens to be the tangent straight line to the circle C. But again, the point P belongs to two circles at once, the circle C, the circle Q, and thus we will conclude that in this case the points C1 and C2 are the inverses of each other under the inversion of the parent plane with respect to the circle Q, again with positive power. If anything is not clear, then by all means do ask your questions in the comment section. And again, if you missed or something is not clear about verbal formulation of the theorem number 40, then you can always download the free PDF file, or the chapter number 9 on which this lecture is based. And the link to that chapter is in the comment section to this episode. The next theorem, the theorem number 41, is a straightforward consequence of the previous two theorems, the theorem number 39 and the theorem number 40. As such, the theorem number 41 claims that if two circles C and Q are orthogonal, implying, of course, that the two circles at hand are coplanar, then the circle C is invariant under the inversion of the parent plane with positive power with respect to the circle Q, and the circle Q is invariant under the inversion of the same plane with positive power, but with respect to the circle C. Again, we suggest that you try to generate a proof of this theorem on your own, and in order to help you do that, I have put together a small animation using the free software called GeoGebra, an animation that hopefully addresses the technical essence and the heart and the soul of the theorem number 41. Our proof of the theorem number 41 is not that complicated, and it amounts to looking at the results that we generated during the proofs of the theorems number 39 and 40 in a slightly different and more generalizing way. That is, during the proof of the previous theorem, we noticed that if we're given two coplanar circles that are orthogonal with respect to each other, then each such circle partitions the other circle into two distinct non-overlapping arcs, an inner arc and an outer arc. And the meaning of the words inner and outer is precisely what we think it should be. For example, if we temporarily take our frame of reference, so to speak, to be the green circle C, then that green circle C partitions the red circle Q that is orthogonal to the circle C into two distinct non-overlapping arcs. The outer arc that runs this way over here, when it is unionized with the first point of intersection of these two circles and the second point of intersection of these two circles, and when these two points also unionized with the inner arc or the set of points of the circle Q that are located strictly inside of the circle C, then this union of two arcs and two distinct points completely produces the original circle Q. And we already noticed, based on the theorem number 40, that the point, if we, for example, draw a second as we shown in the proof of the theorem number 40, then we will see that technically that means that every point of the circle Q that belongs to the inner arc, to its inner arc shown over here, is taken into a unique point that is located strictly on the outer arc of that circle, and conversely, every point that belongs to the circle Q and that is located on the outer arc, outer with respect to our circle C, that point is taken into a unique point that is located on the inner arc of that circle Q. In other words, in plain English, inner points are taken into the outer points are taken into the inner points. All the time, these points belong to one and the same circle Q, and when the power of inversion is positive, in one of our early theorems, we proved that each and every point that belongs to the circle of inversion, which is now played by the circle C, is what? It is fixed or stationary, remains where it is. As such, the two distinct points over which two orthogonal circles intersect, they will remain where they are. And under the inversion of the ambient plane with positive power with respect to the circle C, almost every point that belongs to the circle Q gets moved or rebuilt in a non-trivial way, with the exception of the 2 points where these two circles intersect, because these 2 points remain stationary or fixed. But that still means that even though the circle Q gets rebuilt in such an interesting way, that circle still remains the circle Q itself, and that precisely means that this circle remains invariant under the inversion of the ambient or parent plane with positive power with respect to the circle C. And if we repeat the same argument, but we swap the rows of these two circles and we step into the frame that is our circle Q, we will see that the circle Q partitions the circle C into two distinct and non-overlapping arcs. The outer arc, the 2 points of intersection of these two circles, the inner arc, and the union of all these 2 arcs and 2 points completely makes up the original circle C. Then again, we will see that under the inversion of the parent plane with positive power with respect to the circle Q, every point of the circle C that sits on the inner arc is taken into a particular point that sits on the outer arc of the same circle C, and conversely, each point that belongs to the outer arc of the circle C is taken into a unique and particular point that belongs to the inner arc of the circle C. Again, inner and outer. The meaning of inner and outer is assigned by the mutual juxtaposition of these points with respect to the circle Q. Again, because the power of inversion is positive, the points where the two circles intersect, even in this case, will remain where? Well, in this case, they will remain on the circle of inversion Q. They will be stationary or fixed. They will be here, and otherwise, these points will also, as the points that belong to the circle C, will remain fixed, but otherwise the circle C will get rebuilt in a non-trivial way. But despite the fact that all the other points will be shaken and stirred or moved in a non-trivial way, the circle C will still be taken into itself, and that precisely means that the circle C remains invariant under the inversion of the parent plane with positive power with respect to the circle Q, and that completes the proof of the theorem number 41. And at this point we observe that the theorems 39, 40, and 41, the last three theorems that we proved, applied precisely to the case when the inversion of the plane with respect to the circle was with positive power. And in the next two theorems, the theorem number 42 and the theorem number 43, we will investigate what happens to circles when the power of inversion is negative. It should be evident that the direct analog of the theorems 39, 40, and 41, when the power of inversion is negative, of course, do not hold true. This will not work when the power of inversion is negative. But in its spirit, it is possible to construct two theorems that are converses of each other that address this similar situation when the power of inversion is negative. That is, in the theorem number 42, we will prove that any circle, such as the blue circle Q, shown over here on the right side, that passes through any two diametrically opposite points, such as this point and this point, that belong to any circle, such as the white circle C shown on the left, is invariant under the inversion of the parent plane with negative power. Here we pay attention, with negative power, with respect to the circle C, with respect to the circle which houses the two diametrically opposite points through which the original circle Q passes. In order to help you generate a proof of this theorem on your own, I have put together a small animation using the free software called GeoGebra, an animation that hopefully captures the heart and soul and the technical essence of the theorem number 42. Please take a look. For a proof of the theorem number 42, we first name the 2 points where the sample circle Q, shown in blue on the right, and the sample circle C, shown in white on the left, intersect as P1 and P2 for definitiveness. Next, as shown in the first step of the outline of our proof, we construct a straight line named lowercase p that is perpendicular to the diameter P1, P2 through the center of the circle C. Now, because of the juxtaposition of these simple circles Q and C, it is evident that their centers will be distinct, number one. Number two, forgetting for a moment that the points P1 and P2 belong to the circle C, if any circle in general passes through 2 points, then the set of points which play the role of the centers of such circles that pass through the points P1 and P2 belongs to where? It belongs precisely to the perpendicular bisector of that line segment, and in this case, this role of the perpendicular bisector of the line segment P1, P2 is played precisely by our straight line lowercase p. That straight line will house the center, which is not shown over here, but it will house the center of the sample circle Q. And as the second observation, that straight line P will intersect our sample blue circle Q at two distinct and evidently diametrically opposite points, the point A and the point A prime N. Next, we will observe that the angle, for example, A P1, A prime 1, because it is a circumference angle that subtends the diameter of the sample circle Q, must be what? That angle must be right pi over 2 radians or 90 degrees due to the Thales' theorem, or the corresponding theorem from Euclid's Elements Book 3, where Euclid develops the theory of circles. Now we see that the straight line P1, P2, a diameter of the circle C, plays the role of what? It plays the role of the height of the right triangle A P1 A prime N, that is drawn from where? From the interior right angle onto the base of the triangle A prime N, and by the corresponding theorem from Euclid's Elements Book 6, Proposition 8, which we basically proved by hand, if you will, early on in our earlier lectures. In that theorem, Euclid proves that all three right triangles of interest in this case are actually similar. The parent triangle A P1 A prime N and the two smaller right triangles A O P1 and P1 O A prime N. And in this case, for our proof, we need to pick the two smaller triangles. They will be similar, as shown over here. The triangle AOP1 is similar to the triangle P1OA prime N. And right away, we turn around and bring in the Euclid's Elements Book 6, Proposition 4, in which Euclid proves that in similar triangles, the lengths of the sides about equal angles form one and the same proportion, where the corresponding sides lie opposite equal angles. And in these smaller triangles, I've highlighted the equal angles. Let's say the angle alpha with red, and the angle beta with green, two green arcs over here. And using this distribution of the magnitudes of the interior angles in these two similar triangles, we construct the corresponding proportion. The length of the side OA that lies opposite the red angle will correspond to which side? To the side OP1 that lies opposite the corresponding red angle in the similar triangle. And then the length of the side OP1 will correspond to the side that lies against the green angle in both triangles, OA prime N. And because in this case the length of the line segment OP1 is exactly r, the radius of our circle C, then from that proportion, by cross multiplying, we have it that the product of the distances from the point O to the point A and from the point O to the point A prime n is precisely r squared. And what does that mean? Well, we go back to our definition 1 and recall the three conditions that we imposed on that definition. The points A, O, and A prime n must be coplanar, which they are. They must be collinear, which they are. And the corresponding distances must honor the relation that is the workhorse algebraic manifestation or algebraic formula for our inversion of the real plane with respect to a circle. All three conditions are honored, and that means that the points A and A prime n are definitely the inverses of each other, but we also see that these points are located on the opposite sides of the center of inversion of the point O, or using the axioms of geometry due to the German-born mathematician Hilbert, the point O here is in between the points A and A prime n, and that means that these 2 points are the images of each other under the inversion of the parent plane with respect to a circle C, but with precisely negative power. That's the important bit. Now, lastly, this was the special case for this conveniently located points A and A prime n. But then on the circle Q, we pick any other point that is distinct from A prime n, P2, or P1. Let's say point B shown over here. Then we construct a straight line through this randomly picked, let's say, point B and the point O until that line segment intersects the circle Q at the second point. We will name the point B prime n. And what can we do then? Well, this is book 3, proposition 35 by Euclid from his Elements, otherwise known as the intersecting chords theorem. And as Euclid puts it, you remember that in any circle, the rectangles, if you will, on such intersecting chords must be equal one another. In modern speak, it means that the product of the distances from the point O to the points A and A prime shown over here must be exactly the same as the product of the distances from the point O to the points B and B prime n. And voila, that means precisely that all the other points on the circle Q honor this workhorse algebraic definition of the inversion of the real plane with respect to a circle. And in some sense, even the line segment P1, P2 also can be taken to be an intersecting chord with the diameter A prime n. The same idea holds, and again, that means that our circle C, the white circle C, shown on the left, partitions the circle Q into what? Into 2 distinct non-overlapping arcs. One such arc will be inner arc. Every point on that arc will be sitting precisely or strictly inside of the circle C. All the other points of this arc will be sitting strictly outside of the circle C, and the points P2 and P1, the 2 diametrically opposite points on the circle C, they will, in some sense, exactly partition these 2 arcs, the inner arc and the outer arc. And we see that, just as we showed across these observations, every point on the inner arc of the circle Q is taken into a corresponding unique point that sits precisely on the outer arc of the circle Q, and conversely, every point that sits on the outer arc of the circle Q is taken into a specific unique point that is located on the inner arc of the circle Q. the points P1 and P2, as we know, under the inversion of the plane with respect to a circle with negative power, will do what? They will trade places with respect to the point O. But this is the observation that we will make in the next theorem. And that pretty much concludes the proof of the theorem number 42. Here, however, we have to be careful. Observe that one, the circle C and the circle Q are not orthogonal. The circle C and the circle Q are not orthogonal, and the circle C is not invariant under the corresponding inversion of the parent plane with negative power with respect to the circle Q. So in this case, the direct analogy that we had with the previous theorem, the theorem number 41, is not in place. This is not a direct analog of the theorem number 41 where we dealt with positive power, but as I noted before, in spirit, this theorem is the same. Why is that? Well, in spirit means we still have the invariance of one geometric object, the circle Q, under the corresponding inversion of the real plane with negative power with respect to another circle. So the invariance of a particular geometric figure under a specific transformation is what makes these theorems close in spirit. And now that we proved the theorem number 42, we will take on the converse of the theorem number 42, or the theorem number 43. Being the converse of the theorem number 42, the theorem number 43 claims that if, as I showed over here in red, if a circle Q is invariant under the inversion of the parent plane with negative power, this is important, with respect to a circle, such as the circle C, then the circle Q necessarily intersects the circle C at 2 points, P1, let's say, and P2, that are the diametrically opposite images of each other. Again, one more time here, we take it under the assumption that a simple circle, such as the blue circle Q that is shown on the right, is indeed, somehow we know that it is invariant under the inversion of the parent plane with respect to a circle C with negative power. Then the 2 points over which the two circles intersect must be necessarily diametrically opposite images of each other relative or with respect to the circle C. In other words, if we connect the point P1 and P2 on the circle C, that line segment must necessarily pass through the center O of the circle C. The proof of the theorem number 43 is especially pleasant because the premise of this theorem is quite strong. In other words, if we assume that a circle Q is indeed invariant under the inversion of the parent plane with respect to a certain circle with negative power, then we have no choice but to observe that that means that assumption or that premise translates into the following fact. Any 2 points on the circle Q must trade places with respect to the center of inversion O. In other words, if we take any point on the circle Q, draw a straight line from that point through the center of inversion, That straight line will intersect our circle Q at the second point, and under the inversion of the parent plane with respect to the circle C with negative power, such 2 points must trade places. For example, our sample point B must be taken into the point B prime n, and conversely, the point B prime n must be taken into the point B. This is the technical essence of the statement or the assumption that the circle Q is invariant. But this qualifier, if you will, any, is so strong that we observe that if any 2 points must behave like so, then that means that the points P1 that evidently belong to the circle Q and P2 must also behave that way. In other words, under the inversion of the parent plane with respect to a circle C with negative power, the point P1 must be taken into the point P2, and conversely, the point P2 must be taken into the point P1. All along, these points must be what? They must be collinear with the point with the center of inversion O. But the points P1 and P2 belong actually simultaneously to as many geometrical objects as such objects intersect. And in this case, we have two objects intersect, and that means that the point P1 belongs not only to the circle Q, but it belongs to the circle C. And likewise, the point P2 belongs not only to the circle Q, but it also belongs to the wide circle C shown on your left. And that means that when we look at these 2 points from the reference frame, if you will, of the circle C, what does it mean? Well, these 2 points must trade places in such a way that the line segment that is delineated by these 2 points must contain the center of inversion O. And what do we call 2 points that contain a straight line that passes through the center of a circle? Well, we call it the extremities of a diameter. And that means that in this case, there is no choice but to make one inevitable conclusion that the points over which the circle Q and the circle C intersect must be diametrically opposite points of the circle C with respect to which, with negative power, our sample circle Q remains invariant. Now, this completes the proof of the theorem number 43. And now that we understand that the magnitudes of angles and the tangency points of the interacting curves under the inversion of the real plane with respect to a circle are preserved, we can finally investigate the relationship between the centers of two circles that are the inversive images of each other, and how do these centers of the circles correlate to each other via the center of inversion. As such, in the problem number 10, we're given two circles. For example, let us agree to call these circles lowercase q and lowercase q prime, that we are told are the inversive images of each other with respect to a circle of inversion. We traditionally call this circle of inversion lowercase c. I show a sample circle of inversion in white on your left, and the center of inversion is the center of the circle of inversion, uppercase O. We know that such inversion can be carried out with two powers, with negative power or with positive power. Here I started with a sample diagram that evidently depicts the inversion with positive power, because both inversive images in this case are located on the same side of the center of inversion O, and with this setup, we're asked to find a composition of inversions that takes the center of one circle into the center of the other, and conversely, technically and in general, but due to the symmetry of the situation, it is evident that we can also ask for the composition of inversions of the center of the other circle into the center of the one. Either way works. Here, recall that the corresponding problems that we solved previously, with these problems we figured out how to take a circle, such as the circle Q that does not pass through the center of inversion, and reflect that circle into its image. With respect to a circle C, we actually did it with both positive and negative power, but let us say we do it with positive power. We snap the straight line of centers, which will intersect the given circle at two distinct points. We reflect these points. The point that's closer to the center of inversion will be taken farther out, and the point that is located further away from the center of inversion will be taken closer in. These two reflective images will delineate the diameter. We snap that diameter in half, obtain the center of the image circle, and snap the circle. And through that construction, it is evident that technically, of course, we apply this construction to the circle itself, to the set of points that are equidistant from a fixed point in the given plane called the center of a circle. But even if we try to technically construct the image of the center of that circle, uppercase Q, with respect to a given circle, that point will not be taken into the center of the image. And conversely, if we try, for example, to reflect this circle into this circle, likewise, we know how to do that. Straight line of centers, two extreme points. One point is taken further, this point will be taken further away, this one's closer. Snap again the delineating line segment in two, snap a circle, there we go. But if we reflect the circle Q, the point Q prime in the given circle with the same power, it will not be the point Q. So here in this problem, we're asked to precisely do that. We're asked to find a way, in general, a way to invert the center of one circle into the center of the other, and conversely, the center of the other circle into the center of the one under the given inversion. Again, in both cases, when the power of inversion is positive and when the power of inversion is negative, we will begin with the case when the power of inversion is positive. And sometimes, in order to make sure that everyone in the audience is on the same page, sometimes students say, oh, why don't we just translate the point Q into the point Q prime and game over? You see, this is precisely what we are not allowed to do. In some sense, we are not allowed to do anything but to construct a composition of inversions. And what is a composition? A composition is a sequence of operations such that the result of the current operation or the output of the current operation becomes the input for the next operation. So here, the technical essence of the problem that we need to solve over here is the following. We take it that we have two circles that are the inversive images of each other with respect to a given circle with positive power, let's say, and then to the point Q, let's say, or the point Q prime, it doesn't matter. Let's say to the point Q, we have to apply a certain composition of inversions. Invert, 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 boom. At the end of this composition of inversions, we have to wind up at the point Q prime, and conversely, we have to start with the point Q prime, invert, 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 somehow invert, and boom, we have to arrive at the point Q. That is the technical challenge. So here we need to invent, in some sense, a sequence of inversions of the parent plane, somehow that will take the center of one circle into the center of its inversive image. Again, we recommend that you put this video on pause, walk away, try to solve this problem on your own, and then come back and compare your ideas to ours. When we step into the problem number 10, we need to have a device with which we can act on the center of inversion, as it turns out, in a useful way. And what is one such device? Well, one such device is the inversion of the plane with respect to that center itself, and we know that in this case the center of inversion is taken into the point at infinity, and conversely the point at infinity is taken into the center of inversion. However, in our case, all the points of interest are the so-called finite points. We are not dealing with the points at infinity, and as such we need a slightly different device. And what is such different device? Well, remember our early theorems and problems that we have solved in our course. A straight line that does not pass through the center of inversion is taken into a circle that does what? Into a circle that does pass through the center of inversion, and this is our honing in thinking. This is one fruitful idea that we can fish out from our proverbial web of mathematical knowledge. As such, we begin with a straight line and we attempt to solve this problem in the so-called reverse order. In other words, if at first we want to invert the center uppercase Q of the circle lowercase q into its body, if you will, the center Q prime of the inversive image Q prime, then here we temporarily assume that the problem has been solved somehow. We do not know how, but somehow it was solved, and we found the composition of inversion that starts with the point Q and somehow finds its way into the point Q prime. And now we try to unwind the sequence of steps that will forwardly, hopefully will allow us to construct the solution in the forward flow of causality. As such, we now think, we now have the point Q prime, and we want to, and that point is the center of the circle Q prime, that is the image of the circle Q under the inversion of the parent plane with respect to a circle C with positive power. And now we want to see how can we arrive from the point Q prime into the point Q using nothing but perhaps a clever composition of inversions. Well, to that end, we think as follows. Our straight line that passes through, actually any straight line that passes through the center of any circle is what, by our definition of the angle between two cooperating and interacting curves, is what is orthogonal to that circle. Make sure you can explain why in the format of real-time face-to-face mathematical examination, for example. So here, if we concentrate on the circle lowercase q, we have actually how many? Technically, we have uncountably infinitely many straight lines that pass through its center, uppercase Q, each of which is orthogonal to the circle Q. However, out of this uncountably infinitely many, we pick just one, and that straight line, we will refer to it as the lowercase p. That straight line is perpendicular to the straight line of centers that connect the center of inversion O and, let's say, the known to us, we temporarily assume by temporary assumption, the center Q prime of the circle lowercase q prime. So that straight line is perpendicular to the straight line of centers shown over here. Now we go back to the theorems that we proved and developed in this episode, and what do we say? We say that if our circle Q is orthogonal to the straight line P, then under the corresponding inversion, actually in this case the inversion could be with either power, positive or negative, but in this case we limit ourselves to the inversions with positive power. As such, if the circle Q and the straight line P are orthogonal, which they are, then under the corresponding inversion of the parent plane with respect to the circle C with positive power, their images, the circle Q prime and whatever the image P prime is, they also must be what? They must be orthogonal. They must be orthogonal. That much we know, because the magnitudes of the angles between the cooperating and interacting curves under the inversion of the plane with respect to a circle is what is preserved. But we already know that the image of the circle Q is another circle, Q prime, which is given to us. This is wonderful. But what do we know about orthogonal circles at this point in our course? Well, at this point in our course, we know that a pair of orthogonal circles have the following property. Either one is invariant under the inversion of the parent plane with positive power with respect to the other circle. And in this case, in some sense, we fix the circle Q prime and we claim that our circle P prime, in this case, remember the straight line P that does not pass through the center of inversion, is taken into a circle, the pink circle P prime shown over here, that does pass through the center of inversion. You see, this is how we cleverly, in some sense, found a device that allows us to move, in some sense, the center of inversion, not into a point at infinity, which doesn't help, but into a point that is finite, as such. Because this pink circle P prime is orthogonal to our blue image circle Q prime, it means that the circle remains invariant under the inversion of the parent plane with respect to the circle Q prime with positive power. And what does that mean? Remember that in this case, we have the partition of that circle into two arcs, outer arc, inner arc. So if the straight line of centers, this one, intersects our image circle P prime, the pink circle P prime, at the point O prime for the second time, the first time it happens at the center of inversion, then that means that the point O prime and the center of inversion are what? They are the inversive images of each other under the inversion of the real plane, of the given plane, with respect to which circle? To the circle Q prime. With what? With positive power. That is on the one hand. On the other hand, also, if we go back to our early proven theorems and the problems that we solved early in this case, remember how we constructed the image of a given straight line by synthetic means with the Euclidean tools alone, a straight edge and a compass. What is the point Q over here? This is the point where our straight line, lowercase p, intersects the line of centers. What happens to it? Exactly, this point is taken into the point O prime. This is how we, in some sense, constructed the image, the pink circle P prime. That is how we constructed. And that means that our point O prime, shown over here, O prime, plays two roles at once, as depicted by two arrows, plays two roles at once. Two roles. On the one hand, the point O prime is the image of the point O under the inversion of the plane with respect to the circle Q prime, as we just proved it, because our circles P prime and Q prime are orthogonal, and hence the circle P prime is invariant under the inversion of the plane with respect to the circle Q prime. On the other hand, the point O prime is the image of what? Is the image of the point Q under the inversion of the plane with respect to the circle C. You see, this is the clever and interesting point O prime that plays two roles at once or wears two hats. I'm the image of the point O if I'm reflected in the circle Q prime, and I'm also the image of the point Q if I'm reflected in the circle C. And in some sense, this observation already solves the problem fundamentally. That is, still working in reverse order, we know the location of the point Q prime. We do not know the location of the point Q. How do we invert the point Q prime into the point Q? Q prime into the point Q. Well, this is the composition of inversions. First, we throw the point O, the center of inversion, into its image O prime, using what? Using the circle Q prime as the reflective device. We reflect the point O in the circle Q prime into the point O prime. Why can we do it? We can do it precisely because we know the location of the point Q prime. We have it, we know. And in order to reflect the point O in the circle Q prime, we need exactly to know the location of the point, and we do. So this is done. Once that is done, once the location of the point O prime is on the books, we now flip that point into point Q, but this time in the circle C. You see, in the circle C. That's it. So this is our composition of inversions. 1, 2. And remember, the output of the current operation becomes the input for the next operation. This is a nice and beautiful composition of inversions. Once we have that, we throw all these temporary assumptions out and we generate a sought after forward flow of causality solution. In other words, let's say we know the location of the point Q and we do not know the location of the point Q prime. What do we do? How do we take the point Q into the point Q prime? Well, first we simply swap the circles with respect to which we reflect the center of inversion. This time we reflect the point O. I did not show it over here, so do not be confused. This is not this case. The actual solution is not depicted here, but technically, what do we do? Well, instead of reflecting the center of inversion in the circle Q prime, we reflect it in the circle Q. Again, we will obtain some point O prime, and then we will throw the point O prime into the point Q prime, this point over here, but this time in the circle C. So from O to O prime through the circle Q. So here temporarily the circle Q will play the role of the circle of inversion. We will obtain the point O prime, and then O prime will be thrown into Q prime if reflected in the original circle C, and that completely solves the problem when the power of inversion is positive. And again, I recommend that even though I did not show this diagram over here for this solution, you carry out that construction and witness for yourself that this is indeed the case using your favorite graphing software. Now, in the next segment, we will address the case when the power of inversion is negative. If you understood how the problem number 10 can be solved in case when the power of inversion is positive, then you should be able to solve this problem in the case when the power of inversion is negative on your own. And because we went over the solution of the previous case in great details, I will move through the solution of the case when the power of inversion is negative slightly more expediently. That is, here now that we know that the cat is out of the bag, we right away construct a straight line, lowercase p over here, that is perpendicular to the straight line of centers, or the straight line that passes through the center, for example, of the given circle C, the point O, and let's say the point uppercase Q, which is the center of the circle lowercase q. And in this case, however, because the straight line lowercase p is orthogonal to the circle q, we know that the magnitude of the angles between curves is preserved. Whether the power of inversion is negative or positive, still we have the same exactly implication. If the circle q is perpendicular, is orthogonal to the straight line p, then the images, the circle q prime, and in this case another circle p prime, will be orthogonal. But in this case, we see that how do we obtain the image of the straight line P? Well, here we reflect that straight line in the given circle with negative power. And in this case, if we go back to the previously solved problems and the previously proved theorems, let's say our straight line P intersects the circle of inversion C at the point F1. The image circle of this straight line will be a circle that does pass through the center of inversion. The image of this straight line will be the pink circle P prime. It will pass through the center of inversion, but it will pass through the point, which is what? Which is diametrically opposite to the point F1 on the circle C. So this will be the point that it will pass through. However, it still does not matter to us what is going on with the pink circle P1 in reference to how it was reflected. What is important is the fact that the angles, the magnitude of the angles between the images of these two objects is still preserved, and that means that the pink circle P prime, this circle P prime, will be orthogonal to the given circle, the blue circle that is shown partially, lowercase q prime, that has its center at the point q prime, uppercase q prime. This is the point. And again, remember that even though we obtain the pink circle P prime by reflecting the straight line P that is orthogonal to the circle q prime by reflecting that straight line in the given circle with negative power, still the pink circle P prime and the blue circle Q prime are orthogonal. As such, one of these circles will always be invariant under the inversion of the plane with respect to the other circle. So here, still our observation stands, and that invariance will be here still with the positive power, with the positive power. So from that point on, the rest of the solution is evident. The point O prime, the point where the straight line of centers intersects our pink image circle P prime, this point right here, will still play two roles, but we just have to be careful what is the power of inversion through which this point is obtained. The point O prime is the image of the point Q, The point O prime is the image of the point Q under what inversion? Of the plane with respect to the circle C, but with respect to the circle C, but with negative power. Why is that? Well, that is how the construction of the image in this case works when the power of inversion is negative. Remember that this point where the straight line P and the straight line of centers intersect is thrown outside of the circle C and on the side that is opposite in reference to the center of inversion to the side on which this point sits. At the same time, also because the circles Q prime and P prime are orthogonal, the point O prime will be what? It will be the image of the point O under the inversion of the plane with respect to the circle lowercase q prime, but with positive power. Remember, when the circles are orthogonal, the invariance takes place under the inversion with positive power. So here, the point O prime, O prime is the image of the point O under the inversion of the plane with respect to the circle lowercase q prime with positive power, and from that observation the solution follows. In other words, if we know the location of the point Q prime, in order to synthesize or produce the location of the point Q, we execute the following composition of inversions. First, we invert the center of the circle C, our original center of inversion, if you will, in the circle lowercase q prime, with positive power. I put the lowercase r, just make sure that you understand that this is the shorthand notation for the for positive power of inversion. Technically, I should really say RQ prime, the power of inversion is positive, and we obtain the point, throw the point O inside the circle lowercase q prime into the point O prime, and then we invert the point O prime in the circle C into the point Q, but with negative power, See, the point O prime with respect to the circle C flies onto the opposite side of the center of inversion right here into the point Q, and that is the center of the circle lowercase q. That is the inverse image of the circle, blue circle, lowercase q prime. And conversely, if we know the location of the point Q and we need to find the location of the center of its inversive image Q prime when the power of inversion is negative. Again, knowing this, we now want to recover this. What do we do first? Well, again, we go back to this sequence or this composition of inversions is not depicted over here, but in general, you understand the only difference between these two cases is with respect to which circle we invert the center of inversion first. In this case, we reflect the point O in the circle lowercase q with positive power. Here, technically, I have to say r square q, just to make sure that we are here reflecting the fact that the inversion is carried out with respect to the circle q. We're consistent. And then once we obtain the point O prime, we reflect it in the circle C in the given circle, original circle of inversion, if you will, but this time with negative power, necessarily with negative power, and we obtain the point Q prime. Again, if any of the material here is not very clear, this lecture is based on the chapter number 9 of my free book, Inversive Geometry for All. The link to the chapter is in the comment section. You can click up this free PDF file open in the separate tab in your browser and go over the diagrams and the actual reasoning in the solution of this problem. Meanwhile, we will move on to the final two theoretical notions that we will study in our course, and that is the power of a point with respect to a circle and the related notion of the radical axis of two circles. As such, the notion of the power of a point with respect to a circle is, on the one hand, quite powerful and convenient, and on the other hand, it's not that complicated because we define, as the definition 6 of our course, we will define the notion of the power of a point with respect to a circle algebraically as a formula. We will use the stylized uppercase P to denote the power of a point, and the point in question will be the first argument, so to speak, and the circle with which the power of that point is defined will be specified as the second argument, if you will. So PAQ stands for the power of the point A with respect to the circle Q, and it is defined as the difference of squares of the following two distances. The distance from the given point A to the center of the circle with respect to which the power is defined. Here I use the uppercase Q, and the radius of the circle, again with respect to which the power of that point is defined. In our notation, lowercase d square minus r square translates into the distance from the point A precisely to the center of the circle squared minus the square of the radius of that circle. And amazingly enough, that definition of the power of a point with respect to a circle works in all three distinct cases as we draw our point through the circle of interest. That is, it works when the point A, let's say, is located strictly outside of the circle of interest. It works when the point A is located precisely on the circle of interest. And it works when the point A is located strictly inside the circle of interest. And all these three cases are depicted on the board. Let us go over them one by one. In the first case, when the point of interest is located strictly outside of the circle of interest, then evidently the distance from that point to the center of that circle will be strictly larger than the radius of that circle. And in this case, the difference of two squares can be represented which way? D minus r times d plus r, as shown over here, d minus r times d plus r. All the distances are depicted over here on the left side of your screen. The distance from the point A to the center of the circle Q is depicted with d. Consequently, the distance d minus r will be this line segment over here, and the distance d plus r will be this distance right here. That will be the entire second. And that means what? That means that to this particular point in this particular circle, in this particular case, we can apply the theorem, that's the so-called tangent second theorem. We have it that in this case, the power of a point A with respect to a circle will be a real number that will be strictly positive, because the difference between the distance from that point to the center of the circle and the radius of the circle will be always greater than 0. This will be a product of two strictly positive real number. The result will be a strictly positive real number. And in this case, the geometric interpretation of the power of a point with respect to a circle comes out to be the square of the tangent, drawn to the circle through the point that is located strictly outside of that circle. And we can see that in this case, the angle between the tangent, evidently straight line AT, for example, let's say it touches the straight line, touches the circle Q at the point E, and the radius is right, the angle is right, as is evident by the definition of the tangent. And this covers the case number 1. In the case number two, when the point A is located strictly on the circle of interest Q, then the distance from that point to the center of the circle is precisely r. So here in our algebraic definition of the power of a point with respect to a circle, we'll have a difference r squared minus r squared. This comes out to be 0, a real number that is 0. And in the third case, when our point of interest is located strictly inside of the circle of interest, then the distance from that point to the center of that circle will be strictly less than the radius r. Here we will rewrite our algebraic definition as follows. We will factor out -1 out of the difference d minus r over here in this case, as we had it in the previous case, d minus r, factor out -1, obtain the expression in the parenthesis r minus d times r plus d as depicted over here. So the distance r minus d will be this line segment, the distance r plus d will be this line segment, and then the product of what will we have? We always have the product of a positive real number and a positive real number. The product of any two positive real numbers is a real number, but we have a -1 in front of it. So in this case, algebraically or numerically, the power of a point with respect to a circle will be a real number that is strictly less or smaller than 0. But in this case, because our point is located here, it will define a chord. In this case, it will be a diameter, the way we portray it over here. Let's say this diameter is delineated by the points K and L. And in this case, we can bring in the intersecting seconds theorem into this picture, and notice that the product of distances from the point of interest A to the points L and K will be exactly the same as the product of the distances from the point A to the points N and M, where, for example, NM is yet another chord of the circle that passes precisely through the point of interest. And then we can say that the power of the point A with respect to that circle, in this case, when the point A is located strictly inside of that circle, can be represented over here, as shown over here, negative sign in front of the product of the distance AK times AL, or due to the intersecting seconds theorem, it's the power of the same point can be represented as negative with the, we take this product with the minus sign in front of it, so negative product of the distances from the point A to the point M and from the point A to the point N. That is, these three cases cover all possible scenarios of the mutual juxtaposition of the point of interest A and a circle of interest Q that has the, let's say, uppercase Q letter as its center, and using that notion of the power of a point with respect to a circle. On top of that notion, we can build up another notion that is known as the radical axis of two circles. That is, as the definition number 7 of our course, we will take it that the radical axis of two coplanar and non-concentric circles is the set of all the points in the parent plane, the powers of which with respect to both of these circles is one and the same. That is, let us assume that we're given two coplanar circles, such as the circle Q1 and the circle Q2, and these coplanar circles are not concentric. Then, the way the theory goes, we should be able to find, for example, a point, such as the point A1, and that point A1 has the following property. The power of the point A1 with respect to the circle Q1 is a real number that is one and the same as the power of the same point A1, but with respect to the circle Q2. In other words, we compute the power of the point A1 with respect to the circle Q1. We compute the power of the point A1 with respect to the circle Q2. We obtain two real numbers. If these two real numbers match, then we put the point A1 in the bag. That point belongs to the radical axis of two coplanar non-concentric circles. And then we move on. We walk around the plane, we somehow find another point, let's say the point A2, and it so happens that the two real numbers, to which we refer as the power of that point with respect to circles Q1 and Q2, match. Boom, we put this point in the bag, we keep moving on, and we thus walk around the plane and we pick and we collect all the points for which the two real numbers that we compute according to the definition of the power of that point with respect to both circles, they match. Now that we understand the definition of the radical axis of two coplanar and non-concentric circles, we will prove our final theorem of the course, the theorem number 44, which claims that the radical axis of two coplanar and non-concentric circles is a straight line that is perpendicular to the straight line of centers of these circles. In the final theorem of this course, the theorem number 44, we will prove that the radical axis of any two coplanar and non-concentric circles is a straight line that is perpendicular to the line of centers of these circles. A proof of the theorem number 44 that is perhaps the most succinct, the most compact, and the most straightforward is algebraic, and this is where we admittedly step away a little bit from our pure synthetic geometry-based introduction to the inversive geometry of the real plane. But in order to keep the size of this lecture manageable, we will still go with the algebraic proof of this theorem, and this proof will unfold as follows. Because our two given circles are coplanar, that means that both of these circles belong to one and the same ambient or parent plane, and in that plane there's always possible to construct an orthogonal coordinate system as follows. Because our two circles are unconcentric, that means that the points that are the centers of these circles, let's say the sample point Q1 shown over here and Q2 shown over here, are distinct. And through any two distinct points, there passes a unique straight line, and this is precisely this straight line that will play the role of the x-axis of our future coordinate system. This observation is important because in a very small number of minutes we will arrive to an equation that makes sense in that coordinate system, and we will see that the equation of the radical axis of our two circles is precisely a straight line, and not only that, it is a straight line that is perpendicular to the straight line of centers. In other words, through the distinct centers of our two circles, which I do not show on this diagram in order to avoid the clutter, there is always possible to construct the so-called unique line of centers, or the straight line that passes through the centers of the circles. And precisely that straight line of centers will play the role of the x-axis in our orthogonal coordinate system. Moreover, again, because the circles at hand are non-concentric and their centers are distinct, we take that the distance between these centers, or the distance between the points Q1 and Q2, is arbitrary, but it is finite. That is why it is always possible to cut this distance meaningfully, in a meaningful way, in half. And the half distance between the points Q1 and Q2, we will give it a name, the algebraic symbol A. A and A as a strictly positive real number. Now, the perpendicular bisector of the line segment Q1 and Q2 will precisely play the role of the orthogonal y-axis of our coordinate system, x, o, y. Consequently, the point where the x-axis and the y-axis intersect under a right angle will be the origin of our coordinate system. This will be precisely the dead middle of the distance between the centers of our circles, the points Q1 and Q2. And in such a, for this coordinate system to be complete, technically and pedantically, we need to specify the unit line segment. But again, in order to avoid the clutter, I do not show the unit line segment, but we agree that it is implicitly here, and the scale on both, the scale of distances on both axes is one and the same. 1 unit of distance along the x-axis and exactly the same 1 unit of distance along the y-axis. Now that we have all these constructs in a row, we can in place, we can say that, for example, pedantically, the coordinate of the center of the second circle, the point Q2, will be what? A0. And again, the coordinate of the point Q1 will be what? Negative A0, because these points precisely sit on the x-axis. Next, we take an arbitrary point, such as the point A, in our coordinate system in the plane, and we agree that the coordinates of this point will be, again, some two real numbers, x and y. Technically, here, by placing the point on the diagram, we implicitly lock in a certain, in a way, synthetic geometry, because from this synthetic geometry the underlying algebra will flow. But the claim over here is that regardless of where we place the point A, in the first quadrant of our coordinate system, second quadrant, third quadrant, or the fourth quadrant, the beat, the flow, the spirit of the technical essence of the proof will always unfold in the same way. So here, for demonstration purposes, we place this point A, an arbitrary point, in the first quadrant. But again, I will leave it as an exercise to the viewer to place this point in the remaining quadrants, the second quadrant, the third quadrant, or the fourth quadrant, and see what the algebra leads to. And the fearless prediction here, this algebra will lead to one and the same result that you will see over here in a few minutes. And we take it that d1 is the distance from the point A to the center, the point Q1 of the first circle, the circle lowercase q1. Again, I do not place this circle on the diagram in order to avoid the clutter. There is no need for it. And d2 is the distance of the same point A, but to the center, the point Q2 of the second circle, lowercase q2, which again I do not show to avoid the clutter because we do not really need that. Now we go back to our algebraic definition of the power of a point with respect to a circle, and we construct our first real number called P1, which is the power of the point A with respect to the first circle lowercase q1, which is the difference between the squares of d1 and r1, r1 being the radius of the first circle lowercase q1. I do not show that radius, is just the clutter that we do not need, and it is clear purely algebraically what is the name of the real number P1. Then we do the same thing. We construct the second real number called P2, which is the power of the point A with respect to the distinct coplanar and non-concentric with the first circle, the second circle called lowercase q2. And that power, that real number, is this difference of squares shown over here, d2 squared minus r2 squared. Wonderful. Once we do that, next step, what are we after? We're after the radical axis of these two coplanar and non-concentric circles. And in the previous segment, what did we say about this radical axis? It is a set of points in the parent plane, each of which has the following property. The power of that point with respect to both circles is the same. So in other words, if our two real numbers, P1 and P2, match, then that point belongs to the radical axis of these two coplanar non-concentric circles. Well, that is what we do. We grab the algebraic definition of the first real number, we grab the algebraic definition of the second real number, and we equate them. d1 squared minus r1 squared is equal to d2 squared minus r2 squared. Now, here's the thing. All the numbers in this case, in this relation shown over here, are constant. it means that their squares are constant and the corresponding differences are constant. But here we execute the following maneuver. Look at this. The square of the distance d2, we move from the right-hand side of this relation to the left-hand side. On the right-hand side of this relation, this number was with the plus sign. It jumps over to the left-hand side with the minus sign. d2 squared with a minus. We do the same maneuver to r1 squared. Here on the left-hand side of this relation, this number with a minus sign. And when that number flies over the equal sign and lands on the right-hand side, it loses the plus sign, loses the minus sign, gains the plus sign, and we have this nice difference shown over here. Again, because d1, d2, r1, r2 are constant real numbers, which means what? That means that the radii of these two circles that are coplanar and non-concentric is fixed, is one and the same. Their location is fixed, and the point A is also fixed. So the distance d1 and the distance d2 are also fixed. So these differences of squares shown over here, d1 squared minus d2 squared, is the same as the difference of these squares, r1 squared minus r2 squared. As a syntactic sugar, we name this difference as k, which is a constant real number, which, without the loss of generality, can be taken to be what? Larger than or equal to 0. Why is that? Why this requirement can be imposed? Well, this requirement can be imposed because of the symmetry of the indexes in this relation. Look at this. d1 on the left, r1 on the left. d2 on the right, r2 on the right of the minus sign. So let's say it so happened that the radius r1, let's say, strictly smaller than the radius r2, so this difference of squares comes out to be negative. Well, uniformly, we swap the indexes, or basically rename. The circle that used to be 1 now becomes circle 2. The circle that used to be 2 becomes 1. And voila, we have a smaller square subtracted from a larger square. The requirement that this number is greater than or equal to 0 is honored anyway. And now we step away from pure algebra a little bit into synthetic geometry, and we bring in the so-called Pythagorean theorem, or Euclid's Elements, Book 1, Proposition 47, and we write down the relationship between the distances d1 and d2 in terms of, in some sense, synthetic geometry. Because the Pythagorean theorem is formulated in such a way that it doesn't know anything about any coordinate system whatsoever. It is a pure metric, if you will, relationship between the sides of a right triangle and its hypotenuse. So here, the distance d1, or the line segment AQ1, forms a hypotenuse of the right triangle. Which one? Q1, X, A. One side, the other side, hypotenuse. So the square of the hypotenuse, d1 squared, is equal to square of one side. What is the length of this side? Y squared, plus the square of the other side. What's the other side? Well, it's the length of A, half distance between the centers of the circles, and the coordinate x, x plus A squared. And what do we have for the distance d2? Same thing. We pick the following right triangle, Q2, X, A, this triangle. And to that triangle, in some sense, ripped somewhat out of the coordinate system, we apply the Pythagorean theorem. The square of the hypotenuse, d2 squared, is the square of one side, y squared, plus the square of the remaining side. What is the length of that side? X minus A. You see, X minus A gives us this distance. X minus A. That's it. Game over. We now unpack this middle school algebra and spell out what we have encoded here as a sum of two numbers squared and the difference of two numbers squared. We get these two expressions. Again, everything is straightforward, nothing beyond middle school algebra. If you were to prove this theorem on your own, after you construct these two relations, what do? Well, you go back to this. You capitalize on the fact that we have a constant over here. We, in some sense, do not care what its actual value. We know it's a constant real number. So from d1 squared on the right-hand side, we subtract d2 squared, which is spelled differently here. And what do we see? Well, d1 squared minus d2 squared is equal to, look at this, y squared, cancel, x squared, cancel, 2ax minus minus or plus 2ax accumulate, a squared, cancel. So what does it mean? It means that d1 squared minus d2 squared is equal to 4ax, which is what? The difference of the squares is a constant real number. Look at this. Game over. From this relation, we write down the expression for x. X is equal k over 4a. Boom, game over. Now, a is a strictly positive real number. Why is that? Well, because the centers of our circles are distinct. They're different. There is some non-zero distance between them. Cutting this distance in half always produces a strictly positive real number. We call it number a times another strictly positive real number 4. The product of two strictly positive numbers, real numbers, is a strictly positive real number. So now the name of this constant real number, which we refer to as k over 4a, and we can designate as x0. The value hangs in the balance of what k is. We know k could be 0, so then in this case, x will be 0. So the straight line here will run this way, 0. Or otherwise, it is strictly larger than 0. It will be strictly positive real number as well, and the game is over. X equal to x0, which is in our case, like we said, non-negative real number, is an equation of a straight line, first of all, and not only that, it's an equation of a straight line that is what? That is perpendicular to the x-axis. But going back to the assumption that we made a few minutes ago, that x-axis is what? That x-axis is the straight line of centers. Consequently, we prove our theorem that the radical axis of any two coplanar and non-concentric circles is a straight line that is perpendicular, or in the highbrow language, orthogonal, if you will, to the line of centers of these circles, and the game is over. We're done with the proof. If anything is not clear, ask your question, but now on the practical side, we want to learn how to physically construct that radical axis, or in some sense, how to chase down the exact value of this mysterious for now number called k over 4 times a, or x0. How do we find it? Well, it turns out it is possible to find that number with nothing but the Euclidean tools alone, with a compass and a straight edge. And in the next short 4 segments, we will do exactly that. We will figure out how to construct the radical axis of two circles in all 4 meaningful juxtapositions of the circles with respect to each other. That is, when the circles intersect over 2 distinct points, when the circles touch at a single unique point, when the circles have 0 points in common, but neither circle contains the other. And the fourth case is when both circles have 0 points in common, but one circle is contained by the other. That is, first we will consider the case when any two coplanar non-concentric circles intersect each other. And when two coplanar non-concentric circles intersect, They do so over two distinct points, such as the points A, shown over here on top, and the point B, shown on the bottom, where the sample circle Q1, shown on the left, intersects the sample circle Q2, shown on your right. In this case, we claim that the radical axis of any two coplanar non-concentric intersecting circles will be a straight line that passes precisely through the distinct points over which these two coplanar non-concentric circles intersect. Why is that? Well, first, we compute the power of the point A over which these two circles intersect, and we see that this power must be 0. Why is that? According to our algebraic definition, such a power is the difference between the square of the distance of that point to the center of that circle. In this case, that distance will be r1, the radius of the circle Q1, and the radius of the circle, r1. r1 squared minus r1 squared is 0. And the same exactly idea applies to the power of the point B with respect to the first circle, Q1, and the second circle, Q2. Either way, in either case, the powers come out to be 0. 0 is equal to 0. 0 is equal to 0. The condition for the point in the parent plane to belong to the radical axis of such two coplanar non-concentric circle is honored. And that's one thing, but if we know that a certain curve must pass through two distinct points, that doesn't really say much. It would be nice to know the exact shape of the curve, and according to the theorem number 44 that we just proved, the radical axis of any two coplanar and non-concentric circles is a straight line, number one, and not only that, it is a straight line that is perpendicular to the straight line of centers of these two circles. Question: which straight line which passes through the points A and B will be perpendicular to the straight line of centers of our two intersecting circles? Well, this precisely is the straight line that passes through these 2 points. Game over, proof is complete, and in order to keep the size of this lecture manageable, again, I will not be proving that fact. I will leave it as an exercise to the viewer, but here as a hint, you will construct 2 auxiliary triangles. You will show that these triangles are congruent, which means that the corresponding angles will be equal. You will look at the smaller triangle, 2 triangles. By side angle side, these triangles will be also congruent. The corresponding angles will be equal, and then when one straight line stands on the other straight line in such a way that the angles on either side are equal, this is what Euclid calls a right angle, and all right angles are equal. This is one of his early axioms, and this completes the proof of the fact that the radical axis, shown in red, of any 2 coplanar non-concentric intersecting circles is precisely the straight line that passes through the 2 distinct points over which the said 2 circles intersect. Next, we will look at the case when 2 coplanar non-concentric circles have precisely 1 point in common, or when such circles touch. In the second case, we claim that the radical axis of any 2 coplanar non-concentric circles that touch at precisely 1 point, let's say the point T, will be the straight line shown in red over here that passes precisely through the single point of tangency of these 2 coplanar non-concentric circles, regardless of the type of tangency, external, as shown over here on your right with the circle Q2, or internal, shown over here on your left with another copy of the circle Q2. For a proof of that statement, we again go back to the definition of the power of a point with respect to a circle, and we compute the power of the single point of tangency, or the single point that both of these coplanar non-concentric circles have in common. Let's say we name that point T for demonstration purposes. The power of that point T with respect to the first circle, Q1, with respect to the first circle, Q1, that is still shown on your left over here, Q1, will be what? That power will be 0. Why is that? Because the point T belongs precisely to that circle. That was the second case in our definition of the power of a point with respect to a circle. Now, the power of the same point T with respect to the second distinct coplanar non-concentric circle Q2 that touches our first circle externally or internally will also be what? Will also be 0, precisely because that point of tangency also belongs to the circle Q2, whether that circle touches the first circle Q1 internally or externally. 0 is equal to 0, so we know definitely the point T, the single point of tangency of our two coplanar non-concentric circles, definitely belongs to the radical axis of these two circles. Now we bring in the theorem number 44 that we just proved, according to which the radical axis of any two coplanar non-concentric circles is first a straight line, and second is a straight line that is perpendicular to the straight line of centers of these two circles. So now we have the following question. Which straight line, or how many straight lines, pass through a point on a given straight line in such a way that all these straight lines are perpendicular to the original straight line? Well, in the Euclidean geometry, it's only one such straight line perpendicular to the original straight line or the straight line of circles, and that statement can be proved in a number of different ways. In order to keep the size of this lecture manageable, I will leave it as exercise to the viewer to prove it, but from a highbrow perspective of mathematics, we can take the tangent to a given curve as the limiting position of a second, and that limiting position is unique, there is only one. Or if we step away from the higher machinery from the machinery of a little bit higher mathematics and step back into the elementary synthetic geometry, then one way to prove that there is only one straight line passes through a given point that is on the straight line, and that straight line is perpendicular to the original. That proof can be constructed by contradiction. Construct the second, for example, straight line that somehow passes through the point, let's say T, and is still perpendicular to the straight line of centers, and you should be able to derive a contradiction. Meanwhile, we will move on to the third case, when two coplanar non-concentric circles have precisely 0 points in common, but neither circle is contained within the other. In the third case, when any two coplanar and non-concentric circles have precisely 0 points in common and neither circle is contained by the other, that means that in the parent plane the two circles are completely separate with respect one to the other, and in this case the exact location of the radical axis of such two circles can be recovered if we recall our interpretation of the power of a point with respect to a circle that we made several segments ago when we considered the very first case. It was shown on the left side of the board. You can rewind this video and go back to that episode and recall that we stated that when the sample point or the point of interest is located outside of the circle of interest, then through the means of synthetic geometry, the interpretation of the power of that point with respect to that circle is what? Is the square of the length of the tangent drawn through that point to that circle. And in this case, because we have 0 points in common, and the condition that neither circle is contained by the other implies that in this case we can construct actually how many? Well, it will be 4 distinct, in general, it will be 4 distinct tangents that are separated or sorted into 2 distinct piles, the external tangents and the internal tangents. And for those of our viewers who are new to this channel, we actually solved this problem of constructing both external and internal tangents to 2 such circles in season 2, episode 6. That was our season 2 math problem number 9. You can download the season guide for the second season, find the link and look at the solution. So the problem of constructing an external tangent to both circles is completely solvable with Euclidean tools alone. That's why the solutions are quite elegant and they can be done, obtained in several different ways. But for us, it doesn't matter. We're not going to deep dive into it. Know this, that on this channel, in a public setting, we solved that problem. Season 2, episode 6. This is season 2 math problem number 9. Season guide for number 2. The links is in the description to this video. Click it open or find that episode on your own. Watch it. You will see how this problem is solved. So here the question is, if the radical axis of these 2 circles in this specific case is a set of points, the square of the length of the tangent from each of which is the same to both circles. And how do we find that set? Well, it is actually very straightforward. All we do is, again, construct just one out of two distinct external tangents that in general will converge or intersect at the center of homothency for these 2 differently sized circles. We pick one, let's say this one. Tau x stands for the external tangent. Here, this external tangent will touch the circle Q1 at the point T1, and that external tangent will touch the circle Q2 at the point T2, shown over here. Like I said before, that task is completely solvable with Euclidean tools alone, with a compass and a straight edge. This is completely doable. We show all the steps in season 2, episode 6. And now after that, we simply cut that line segment, T1, T2. We cut it in half, we bisect it, and we find it's that middle point M, such that the distance from the point M to the point T1 is exactly the same as the distance from the same point M to the point T2. This condition holds. And now, what do we do next? Now, once the synthetic geometry reasoning is done, we go back again to our theorem number 44. Recall that the radical axis of any 2 coplanar non-concentric circle must be a straight line that is perpendicular to the straight line of centers. And now we know one point, here is the point M, the midpoint of the common external tangent, that has the same power, or in the terms of synthetic geometry, the same square of the length of the tangent to the circle number 2 to the circle number 1. So our straight line must pass through that point M, the midpoint of the common external tangent constructed to both circles. Now what? Well, through that point, how many straight lines can be constructed that are orthogonal or perpendicular to the straight line of centers? Again, only one straight line can be constructed. And that straight line is precisely the radical axis, shown in red, is the radical axis of 2 coplanar non-concentric circles that have 0 points in common, and neither one circle is contained by the other. One more time, this radical axis, shown in red, is constructed as follows. Construct one external tangent that is common to both circles. obtain the points T2 and T1 where this tangent touches our circles, cut that tangent in half, obtain the point M, and construct a straight line through the point M that is orthogonal or perpendicular to the line of centers. Game over. Here again, in order to keep the size of this lecture sizable, I will not go into the proof, but idea is the same. You can construct the proof that only one perpendicular straight line through a point that is not on the given straight line can be constructed by contradiction. Assume that through this point there is another straight line that is also somehow perpendicular. So we have a triangle that has two right angles, and then 90 plus 90 is already 180, but by the corresponding theorem in Euclid's Elements Book 1, the magnitude of the interior angles of any non-degenerate plane Euclidean triangle must be what? 180 degrees or pi radians. So we already have 90 plus 90 is 180. 180 must be equal to 180. So the angle at the vertex M must be what? 0. So boom, only one straight line that is perpendicular to the given one and passes through the point not on it can be constructed, and that straight line is precisely the radical axis of two coplanar non-concentric circles that have 0 points in common, and neither one is contained by the other. And now we will consider the final case when we have two coplanar non-concentric circles that have 0 points in common, but one circle is contained within the other. Lastly, we consider the case when any two coplanar non-concentric circles have 0 points in common, and one of the circles is contained by the other. Again, without the loss of generality, we can say, for example, the circle Q2 shown over here. I try to do my best in order to avoid the clutter, but let's say this is the circle. Where can I put it here? This is the circle Q2, and this over here, nice and neat, circle Q1. Here we will designate the circle Q2. Let us say that the circle Q2 shown inside is completely contained by the circle Q1, and the objective now is to find the radical axis of these two circles using nothing but the Euclidean tools alone. And here we have actually two options, and the solution to this specific problem for this specific juxtaposition of two coplanar and non-concentric circles is an absolutely wonderful, crisp, beautiful, elegant demonstration of the general problem solving techniques, and it amounts to the following. When one circle is completely contained in the other and the circles have precisely, remember, they have precisely 0 points in common, then we cannot really construct a common tangent as we did in the previous case when we capitalized on a geometric interpretation of the power of a point with respect to a circle. When such a point is located outside of a circle, it's the square of the tangent constructed through that point to that circle. Here there is no traditional classical tangent that we construct to these two circles. So what do? Well, we go back, we actually build on the previously solved cases or on the previously solved problem. Let's say we construct an arbitrary circle. Let's call that circle W1, for example. And that circle, the auxiliary circle W or omega1, whatever, it doesn't really matter. However, we construct that circle in such a way that it intersects, one circle intersects both of the circles at hand. That auxiliary circle intersects the circle Q2, and it intersects the circle Q1, at the same time. So now we know that in order to construct the radical axis of two intersecting circles, what do we have to do? Well, we have to just construct a straight line through the points of their intersection. We already proved that little theorem. And we can do it for the pair of circles, let's say W1 or omega 1 and Q2. That straight line is shown over here. That is the radical axis of the blue circle, the helper circle, and the circle Q2. And we can do the same thing, construct a straight line that passes through two distinct points of intersection of the auxiliary blue circle with the outer, let's say, circle Q1. This point and this point. This is this straight line. And here it is evident that what we're using the so-called method of intersecting loci. Here, this blue line right here shows all the points in the parent plane, the power of each of which is the same with respect to which circles, Q2 and W1. And here is the set of all the points in the parent plane. They have the same power with respect to which circles, the same circle W1 and the circle Q1. But the point where they intersect, this point where they intersect will be what? The point which has the same power not only for separate pairs, but for the circles Q1 and Q2. So now we know one point, definitely one point in the parent plane that has the same power with respect to the circle Q1 and Q2, and this is precisely what we want. And now we reduce this problem to the previously solved one when we ask the question, given a straight line, the straight line of centers, how many straight lines can be drawn perpendicular to that straight line, passing through the point not on it, such as the point P1? Well, in Euclidean geometry, only one such perpendicular can be constructed, and that straight line, that perpendicular shown in red, this guy right here, is exactly the radical axis of two coplanar non-concentric circles that have 0 points in common, and when one circle is completely contained within the other. That is how we do it. That is one option. Arbitrary helper circle that intersects all two circles, two auxiliary radical axes. The point where they intersect is the point that we need, and through that point we construct a perpendicular red straight line to the straight line of centers. Boom, this is the radical axis of these two circles in this case. What is the second option? Well, the second option is take this maneuver and use it again. So this solution is shown on the right side of the board, exactly the same setup. The outer circle Q1, shown over here in white, contains the smaller circle Q2, shown also in white. These two circles have 0 points in common, and one of the circles, namely Q2, is completely contained by the other, circle Q1. Here we recognize our auxiliary circle, let's say W1. This is the blue circle here. That's exactly the one that we used over here. Let's say for definitiveness, that's W. And once we use this maneuver and locate the point P1, we pick yet another auxiliary circle. Let's say we will call it W2. And this circle is shown in green. That auxiliary circle also intersects the circle Q1, the outer circle Q1, and the inner circle Q2. Each one of these circles, this auxiliary helper circle, intersects at two distinct points. The same exact logic. The radical axis of the circle W2 and Q1, this one right here, constructed through the two distinct points where these two circles intersect. The radical axis of the circles, the auxiliary helper circle W2, which is distinct from the auxiliary helper circle W1, and the circle Q2, constructed by drawing a straight line through this point where these two circles intersect, and this point, this is this straight line right here. These two straight lines, two radical axes, intersect at the point P2. I showed it in green just to designate, to make it easier for you. And now what do we have? We have two distinct points in the parent plane which satisfy our requirement that the power of this point with respect to both circles Q1 and Q2 is the same, and the point P2 whose power with respect to the circles Q1 and Q2 is also the same. Snap a straight line, and that straight line will be precisely, again, I try to avoid the clutter as much as possible, but that straight line will be, I did not show it originally, but if you guys can tolerate this, that straight line will be, again, perpendicular to the straight line of centers, and that is another beautiful solution. Which one you like, it depends on your taste, on your experience, or maybe on a particular situation. Or from another standpoint, remember that in season 2, episode 6, when we were dealing with these things, we introduced the notion or used the notion of the cost of the algorithm for constructing this or that geometric object using the Euclidean tools alone. So here we have to compute what's the cost of this algorithm versus the cost of this algorithm. And perhaps we can announce the better one is the one that costs less in terms of compass and straight edge operations. So this completes all the cases where the radical axis of two circles can be constructed. We covered all the cases, and in this final case we have two options. And finally, as the very last segment of this lecture, we will note that I will take a second right now to erase what we have on the board right now. Take a good look, make a note. Also, don't forget that this lecture is based on the free chapter number 9 of my free book, Inversive Geometry for All. The link is in the comment section again. Click, pop it open, follow along. If you miss anything, you can always go back to that written material and look at it. But in the next and final segment of this lecture, we will make one more interesting observation that comes from the geometric interpretation of the power of a point with respect to a circle when such a point is located outside of the circle. And we will discover very quickly that the radical axis of two circles, for the most part, there will be one exception, for the most part, is the home for the circles that are orthogonal to both coplanar and non-Euclidean circles, and that situation unfolds as follows. A short animation that you just saw addresses the final theoretical observation that we will do in this course, and this theoretical observation amounts to the following. Remember, in the first case, when we introduced the definition of the power of a point with respect to a circle, we said that if such a point of interest is located strictly outside of the circle, for example, sample point, such a point is located strictly outside of a circle of interest, let's say the circle Q1, then the geometric interpretation of the power of that point with respect to that circle is the square of the length of the tangent drawn through this point to that circle, simply because to that scenario it is possible to apply Euclid's Elements Book 3 proposition 35 or 36, I don't remember exactly the number, but this is the so-called tangent second theorem. Now we go back to our work that we did with the radical axis, and what observations do we make? Well, we already saw that the points that belong to the radical axis can be positioned in three different ways with respect to the parent pair of circles. Such points can be located strictly outside of both circles, Some of these points that belong to the radical axis to these points can be located, in this case, for example, strictly inside both circles. And sometimes such points, as the case on the right shown over here, when the circles touch externally or internally, such points that belong to the radical axis can be precisely on these circles. So now we want to consider evidently the points on the radical axis that do not belong to the inner portion of any circle, but only located strictly outside of all the circles. What can we say? Well, in that case, remember that again, going back to the geometric interpretation of the power of such a point, for example, P, that is located strictly outside of any circle, if from that point we construct a tangent to the circle, and then using the length of that tangent as the radius of the circle, considering just one circle, we will construct a circle that will be what? That circle will be orthogonal to the circle with respect to which the power of that point is measured or computed, let's say. But in our case, we define this geometric object known as the radical axis of two coplanar non-concentric circles as the set of all points, each of which has the same power with respect to both points. And that means that if we pick any point, such as the point P on the radical axis of two circles of interest, and that point is located strictly outside of both circles, or as a degenerate case, on such a circle, then we compute the power. We know by definition the power of that point with respect to either circle must be the same, they must match. In this case, our geometric interpretation is the square of the length of the tangent drawn through that point to either circle stands. That means in this case we take the absolute values itself must match, and if these line segments as tangents are used as the radius of the corresponding circle, then we will see that again, for example, here in my drawing, the line segment PT1 is the tangent constructed to the circle Q1 through the point P. This is tangent, let's pretend. If you do it with the graphing software professionally, everything will look much neater. And the line segment PT2 is the tangent drawn to the circle Q2, again, through the point P, this line segment right here. And again, let's say the point T1 is the point where the tangent to the circle Q1 through the point P touches that circle. And the point T2 is the point where the tangent to the circle Q2 through the point P touches that circle. So now, if we use the fact that these line segments are tangents, that means they are perpendicular to the radius of each corresponding circle. The line segment PT1 is perpendicular to the radius R1, and the line segment PT2 is perpendicular to the radius R2. And what does that mean? Going back to our definition of orthogonal circles, that means that the circle, the sample circle Q, thus constructed, pick any point P, let's say on the radical axis, that is strictly outside or on the circles, construct the corresponding tangents, snap a circle, and that circle Q will be orthogonal to the circle Q1, shown on your left, and that circle Q will be orthogonal to the circle Q2. That circle Q will be orthogonal to the circle Q2, shown on your right. And from that observation, what do we conclude? We conclude that our radical axis, where the situation permits, is the home of unique orthogonal circles constructed, as I will explain right now, that is orthogonal to both of the circles which generated this radical axis. I hope that that is clear. And this case applies to which situations? This case applies to the situations when the circles of interest touch internally or externally, like so, and the point of tangency in this case degenerates into the circle of radius 0. This observation applies to the case where the two circles have 0 points in common and one is contained within the other, because here the radical axis is all outside the circles. This case applies to the situation when two circles of interest have 0 points in common, but neither one is contained by the other. This is the case again. The radical axis here is completely outside of all the circles, outside, outside, and 1 point on. The final case, the radical axis of two intersecting circles, this observation holds for what? For all the points of the radical axis that are on or outside of both circles. So it will be this portion of the radical axis and this portion of the radical axis. And that means that if we pick any point, arbitrary point on the blue lines, which also double up as the radical axis of the corresponding points, construct the tangent straight lines from the point to either circle, and then mark the points of tangency and snap a circle. That circle will be orthogonal to both circles at hand. And this is the animation. That you saw. I put together an animation for you for this case, but I recommend that you also go through this and construct similar animations for all the cases that we show over here. Radical axis, radical axis, radical axis, and the portions of the radical axis. Again, one more time, the algorithm for constructing a circle that is orthogonal to both given coplanar non-concentric circles is the following. Given a point that is located strictly outside or maybe on the circles, we construct the tangent straight line to one circle. It doesn't really matter. We know that by length these tangents will be the same. Let's say we construct a tangent through such a point to the circle 1, or a tangent through this point to the circle 2, and using that point, the chosen point P, as the center and the length of the tangent as the radius, we snap a circle, name that circle Q. That circle Q will be orthogonal to both the circle 1 and the circle 2. Now, this is the final theoretical observation that we will make in this course, and now the real fun begins as we put the developed theory to practice and begin solving problems.